Hi mathematicians, welcome to the Unit 6 Lesson 8 video on Converse parallelogram proofs. First up, let's talk about what we do know about parallelograms based off of the prior lesson. We know that opposite sides of a parallelogram are parallel, so that means that DC is parallel to AB and DA is parallel to CB. The other thing that we know is the opposite sides are congruent. So you can see here that I've labeled with my arrows. We've got these parallel sides that are also congruent and these parallel sides that are also congruent. Okay, we can have these tick marks represent congruence and then our arrow marks to represent parallel. However, when we are working here with our parallel sides, we kind of have the unique tick marks that show the difference between them, right? So DC is a single tick mark with AB showing that these two are parallel, and then DA has the double arc or arrow mark for showing that CB is parallel to it. So we've got parallel sides, we've got congruent sides here. And then we also know that opposite angles are also congruent to each other. We know that the diagonals bisect each other, meaning that DO and BO are the same length, that AO and CO are the same lengths. And then the other bit of information that we do know is that consecutive angles are actually supplementary. So what that means is that if we kind of extend out DC and we extend out AB and we treat DA like a transversal, what it's saying is that our interior consecutive angles right here, they are supplementary. They add up to 180 degrees. The same goes for the angles made with the transversal here with CB, right? These equal 180 degrees. Now, what that means is if these two angles add up to 180 degrees and these two angles add up to 180 degrees, that means all angles in a parallelogram add up to 360 degrees. So keep that in mind moving forward as we work through some proofs. Okay, we have talked about how to prove that quadrilaterals are parallelograms, but what if we know that the angles are congruent? How do we prove that a quadrilateral is a parallelogram? Now, information that we need to know. The addition property of equality, okay, this allows us to add the same quantity onto both sides of an equation. Then we have the consecutive interior angle converse theorem. The converse theorem states that if two lines are cut by a transversal and the consecutive interior angles are supplementary, then the lines are parallel. So rather than lines being parallel at the beginning, like the consecutive interior angle theorem, first we know that we have consecutive interior angles that are supplementary and we have a transversal. Then we know that the lines are parallel. And this is going to matter when we are showing that parallelograms are, or that quadrilaterals are parallelograms. In this proof, we also need to know the side-side-side congruence theorem. So we need to understand that if two triangles have corresponding and congruent sides, that the whole triangle is congruent. And then lastly, down here, we have the substitution property of equality, which basically lets us replace one value with another value that is equal to it. So let's talk about this proof, and let me move myself on over. So we're going to prove that this quadrilateral is a parallelogram. We are given more information than we were given before. This time we are given the information that our angles are congruent. Opposite angles are congruent. So with opposite angles being congruent and us having this diagonal, we have the ability to use our knowledge on congruent triangles to then prove that our quadrilateral is a parallelogram. So how this proof works is we are given that ADC, so ADC, this angle right here, and CBA are congruent to each other. So this angle right here, we've got this angle, and this angle right here. The next one that we know is true is DAB, which is this double arc mark angle right here, and BCA, which is this double arc mark here, okay? So this is information that we are given. We're given that we have these congruent angles. And if you notice, it's the entire angle that is congruent inside the parallelogram. We haven't broken up yet into kind of these smaller triangles yet. Now, based off of the definition of congruence, okay, if these two angles are congruent, that means that they are also equal in measure. So they have the same equal measure. So if this one is 105, this one is going to be 105. Now, moving on to applying information that we just talked about. Okay, remember that that we have these consecutive anterior angles here that are equal to 180 degrees, which means that when we add up all three of them, we get 360 degrees. So that is our third step here. We're talking about how our angles are equal, and that we're talking about how if we add them all up, we get 360 degrees. Now, when we are working with these angles, the cool thing is we've already said that angle ADC is equal to angle CBA, and that DAB is equal to BCA. So we can use that substitution property, which lets us replace equal values. And so we have this equation, right, where we have ADC and CBA. Well, we're taking the CBA and we are replacing it with ADC. Okay, so this CBA becomes ADC. So now we have the measure of angle ADC plus the measure of angle ADC is in this equation. And we do the exact same thing with this DAB and BAC. So originally we had DAB plus BAC, but we've replaced the equal value, which is another DAB. And now we have DAB plus DAB. This gives us two of the exact same angles being added up together. We can, and by the way, you can do this with both sets of angles also, so just keep that in mind. So we have the DAB and we also have the BCA. Either one of those works. And realistically here, instead of having DAC twice, we could have also replaced it with CBA here. Basically, we're just taking these things that are equal to each other and throwing them in to kind of make this problem work for us. Now, having in math, right, when we're adding two things together, so if we're adding, in this case, ADC and ADC together, it's the same thing as having 2 times the angle ADC, okay? So ADC, and I should have the measure in front of this. I'm writing quickly and shortly, but the measure of angle ADC added twice is the same thing as 2 times that value. So they've taken these super long equations here, and they've replaced them with 2 times the measure. So this is saying 2 times the measure of the angle ADC. Okay. So 2 times the measure of the angle plus 2 times. They've taken these and combined them into a multiplication problem. And they've done this for both of them. Now, the second half of this proof is basically we are replacing once again. So let's go back. Okay, so we have 2 ADC and 2 DBA, and then what we're doing here is we're using the division property first. Okay, division property first to get rid of those 2's. So originally we had 2 times the measure of angle ADC plus 2 times the measure of angle DAB. And let me erase this. Is equal to 360. Well, all of these have the value 2 in them. We can take a 2 out of them. So if we divide the whole thing by 2, it gets rid of our 2's in front. And then 360 divided by 2 becomes 180. So now we are left with this single ADC plus DBA. And remember, these are the measures of the angles themselves. So we're adding the two measures of the angles and we're getting 180 degrees. And we've done it for both examples here. Now, we can go back and we can make that assumption that the angles are now supplementary, right? So we can go back to our equation here, and basically what we're saying is that the measure of angle ADC, this one here, and the measure of angle DAB, this one here, okay, we're going back and we're saying, okay, now that we know that they're 180, we're saying that they are supplementary, okay? We're kind of working back, and we're going to end with the fact that these two things are parallelograms. So we now know that they are supplementary. The consecutive interior angle converse theorem is that one that says that if we have that transversal and we have consecutive interior angles that add up to 180 degrees, they're supplementary, then we have parallel lines. So we can say that DC and AB and DA and CB are parallel because their consecutive interior angles are equal to 180 degrees. And by definition of a parallelogram, if we have two sets of parallel lines, we have a parallelogram, okay? So to summarize this problem, right, we talked about how our angles are equal to each other. They all add up to 360. We replaced the values so we could get these two of the same types. We removed the two from all portions of our equation, which show that they're supplementary. If they're supplementary interior angles, then they're parallel, and if they are both parallel, then they're parallelograms. Okay, so that is showing that a quadrilateral is a parallelogram using the angles. Now, what if we wanted to use the sides? So in this case here, we have the addition property of equality again. We can add the same thing to both sides, but we are going to use the alternate interior angle converse theorem. What the alternate interior converse theorem says is that if we have two lines cut by a transversal and their alternate interior angles are congruent, then the lines are parallel. So the last time we showed consecutive angles, right? If we have consecutive angles equal to 180, it's going to be parallel. This time we're going to show that alternate interior angles are going to be parallel. We're also going to use the side-side-side congruence theorem. So all three sides are going to be, if they're corresponding congruent, they're going to be equal. And then we're going to talk about the substitution property of equality. So in this case here, we have our picture, and we are given that opposite sides are congruent. And we want to show that if opposite sides are congruent, that our quadrilateral is a parallelogram. So when we're writing our proof, we always start with the given information, and we're given that DA and CB are congruent, and DC and AB are congruent. By the reflexive property, that means that we can kind of draw this, and actually let's swap it on over to a highlighter. We can use the reflexive property to show that this triangle here, right, that AC is congruent to AC, so it kind of shows two triangles here that are going to be congruent to each other by side, side, side. And then we can also do the same thing here, showing that DB is congruent to itself, to show that we kind of have two unique or two congruent triangles here. So we've got two sets of congruent triangles just by using the reflexive property, showing that these transversals are congruent to each other. So like I said, we're using side, side, side. We know that this and this, these are congruent to each other. I don't know how to write that well, but basically showing that DB and AC is congruent. We can show side, side, side for these two sets of different triangles. Okay, moving on to the second half of the proof. Okay, if we have congruent triangles, we can use CP-CTC to show that their corresponding parts are congruent. So for angle ACD, this triangle, or this angle and CAB, this angle, are going to be congruent to each other by CPCTC, right? We're looking in this case at these triangles here. These two triangles here, right, are the ones that we're looking at, okay? And then we can also show that ADB, so ADB, this angle here, okay, and CBD, this angle here, are congruent to each other because we are looking at the examples for the triangle in which these two triangles are congruent to each other by side, side, side. So now that we have alternate interior angles that are converse, then that means that in this case, right, we have parallel lines. So if alternate interior angles are congruent and we have transversals, then we have parallel lines. So this transversal here is going to show that we have parallel lines, and then this transversal here is going to show that we have parallel lines here. Now, because we have two sets of parallel lines, and realistically I shouldn't have done tick marks, I should have done arrows. Okay, so we've got these parallel lines based off of the alternate interior converse theorem, and so because we have parallel lines, we have parallelograms by definition. Alrighty, those were some big proofs. Make sure to ask questions if you are struggling with them or don't understand a specific part, but ideally you should really know your definitions. Now there's a couple other ways to prove parallelograms. Now we know basically we can use like our congruence theorems to show that if we have congruent triangles, that we have, right, we can use those converse theorems, which is what we just kind of did. The other thing is we know that if we have opposite angles that are equal to each other, then we can work to show that those are parallelograms. And then if we have these congruent sides and parallel sides, we can show that they are in fact parallelograms. Now, mathematically, right, we can do this by showing that we've got congruent sides by plugging in values for our variables. These are variables that we, basically each one of these sides is represented by an expression, okay? And we can plug in these variables to show that we have congruent sides. Now, to do this, we simply just substitute in the values. So for this 11, or for x, we can replace it with an 11 to get 11 plus 10, which is 21. And then we can come down here and do the same thing with the 3. 3 times 11 minus 12, which is going to get us 33 minus 12, which is also going to get us 21. So these two sides are in fact congruent to each other just simply by plugging in known values. We can do the same thing with the y. So we have 4 times y is equal to 10 minus 7. So this gets us 40 minus 7, which gets us 33. And then over here, we can replace or substitute in the 10 into this equation, which gets us 20 plus 15. Did I do my math wrong over here? Is it minus 7? 10, and this is plus 15. Okay, so that means we have 2 times 10 is 20 plus 15, which gets us 35. Okay, which gets us 35. So we have 33 and 35. These are not the same measures. They are not congruent. So we do not have a parallelogram, because if we have, right, basically this means that we have this at a slight angle here, and so we don't have parallel lines because they aren't equal to each other. How do we prove that a quadrilateral is a parallelogram? Using diagonals. Okay, when we're talking about diagonals here, we need to understand that alternate interior angle theorem. So if we have two parallel lines cut by a transversal, then alternate interior angles are congruent. The converse of that is that if we have two lines that are cut by a transversal and the alternate interior angles are congruent, then the lines are parallel. Those are the converse of each other. CPCTC theorem states that if, right, corresponding angles and sides are congruent, if we've got congruent triangles, so corresponding parts are congruent, corresponding parts of congruent triangles are congruent. That is what it stands for. In this proof, we're going to use side angle side. So understanding that if we have a side, sides with an angle in between them, one right after another, if we have corresponding and congruent sides, that we in fact have congruent triangles. Remember that a segment bisector is a line, ray, or segment that cuts another segment in half. So something that cuts a segment in half is a segment bisector. And the vertical angle theorem allows us to state that vertical angles are in fact congruent. So let's look at this proof. Okay, so we are given a quadrilateral with diagonals that are congruent to each other. Okay, so we are given this example where DB bisects AC. That is given information. Okay, by definition of a segment bisector, we know then that we have these congruent sides, right? We have these congruent sides, or congruent segments, I guess, that are split by our other segments. So because we have these congruent sides here, we can use the vertical angle theorem to show that AOD is congruent to COB. Okay, if we're bisecting here, right, we have this vertex O, and we can show that these two angles are congruent to each other. And then we can do the same thing for AOB. Doop, doop. And we've got COD, okay? So these two angles are congruent to each other, and these two angles are congruent to each other by the vertical angle theorem. Now, if you look and see, we've got side angle side congruence with the triangles that are opposite to each other. So the triangles that are opposite to each other are congruent. That also means that their corresponding parts are congruent, right? So now we can say that BCO here, is congruent to DAO, and we can say that CDO is congruent to ABO here. Okay, so now we've got, if you guys notice here, alternate interior angles here and here. These are on opposite sides of the transversal, and they are congruent. So we can use that alternate interior angles theorem to show, and in theory, alternate interior angle converse theorem to show that our triangles have been parallel. Because if we have a line cut, or two lines cut by a transversal, and their alternate interior angles are congruent, that means we have parallel lines. And if we have parallel lines, we have a parallelogram by definition. Alrighty. Other ways to prove that it's a parallelogram, just like before, because we know that parallelograms, we just proved, right, that if we have diagonals that bisect each other, that we have a parallelogram. That's what we just proved. So that means that in this case here, if we can show that x plus 5 is equal to 2x minus 3, right? If these two things are equal to each other, then we have a parallelogram for both counts, right? We have to show both counts. We have to show that x plus 5 is equal to 2x minus 3, and we have to show that 3y plus 2 is equal to 20. Now, to do this, we would just solve multi-step equations. Okay, so I like to remember always split my equal sign. We want our, I'm going to say x's because I have two x's on this side and one on this side. This is going to be my x's side, and this is going to be my number side. So if I want to get rid of my x's, I have a positive one here, so I can subtract an x from both sides. That leaves me with a 5 here, and an x here, and a minus 3 that we still haven't done something with. And then in this case, we don't want numbers on this side. We're minusing numbers, so the opposite is to subtract. So that means that we have our x value would have to be 8 in order for this to be true, and our y value is we have a positive 2. We're going to subtract 2 on both sides, which gets us a 3y equals 18. Divide both sides by 3, and that means y would have to equal 6. For this to be a parallelogram, those would have to be the values of x and y. Okay, that is it for our lesson today. Please reach out if you have any questions, and until next time.